So this is just a warm-up problem, and I hope everybody sees what the pattern is, right? So if I erase the ellipses here, right, so if the pattern continues, we would have another fraction here. We have 2 plus 1 over, and then we continue the process, 2 plus, and this goes on forever. Okay. Yeah, nice to meet everybody. Okay. All right. So I guess I was thinking that you might be able to find a copy of x on the right-hand side of the equality, so somewhere over here. And we can maybe see this better if we rewrite this 2 over here as 1 plus 1, right? So we'll get this 2 over here, we'll write as 1 plus 1, and then the rest of it. If you have an answer, go ahead and you can post it. Okay, so doing that, do you now see a copy of, sorry about that, I need to adjust my positioning here. So does anybody see a copy of x in the denominator? Well, I guess we might as well point it out, since we should probably get started on the real thing here. But if x is 1 plus, and then this recurring pattern here, we see exactly that expression over here. We have 1 plus the recurring pattern, which goes on forever. Okay, so if we rewrite this, we'll have 1 plus, and this here, this expression over here is exactly x. It is equal to x. Okay. Did that make sense for most of you all, you think? Okay. All right. So now, of course, we have a quadratic. Oh, one more time. Okay. So I see that x is equal to 1 plus this expression, this recurring infinite process there. So what we did is we took this 2 and we wrote it as 1 plus 1. Okay. And now I see exactly the same pattern that defines x in the denominator over here. Here's 1 corresponding to this one, plus, and then you have that kind of infinite regress, that block, which, right? So that expression is exactly what x is. All right, very good. All right, so now we could, we have a quadratic essentially. We can multiply both sides by 1 minus x to get rid of that denominator in one fell swoop. 1 plus x, sorry. Distribute. And we notice that, and then the x is, there's an x on either side of the equality, so we can subtract that away from both sides. And we get that x squared equals 2. Okay, so we see that x, so what is x then? Squared, yes. I mean, algebraically speaking, of course, there are 2 solutions for x to that equation. So x is plus or minus square root of 2. But in the context of the problem, it's clearly that, you know, x is equal to 1 plus some positive stuff. So it has to be, well, greater than 1. It's positive in any case. So of course, the only valid solution here is that x is the positive square root of 2. Very good. All right. So I guess a question might be like, what does this have to do with calculus? Well, there is, it's this phrase right here, this pattern or process that continues forever or ad infinitum. Okay. That's very much a hallmark of calculus. We're going to be studying processes that kind of go on forever, and hopefully we reach some kind of culminating limit. Okay. That's one way to relate this to calculus, you know, process of an infinite process. Another thing that I can think of, and it's probably a bad segue, so this is a quadratic equation, correct? So when you think of the word quadratic, and particularly the root of the word quad, what number do you think of? 4, right. Quadrilateral, yeah, four-sided object. Quad on campus is like the the quad on campus, right? So it's 4. So quad, you know, I guess from the Latin or something. Quad is like 4. Okay. So does anybody know why, you know, so where do you see, how does that relate to a quadratic equation? Well, well, because I guess before algebra, right, a lot of things were done geometrically. Yeah, finding the square, right? So I guess another word might be from, I believe it's like the French or something, older French, S quadra, I don't know how to spell it, but something like this. They put an S in front, and that denote, like, if anybody knows French, yeah. If anybody knows French, maybe you can tell me what that means, but I think it implies an action like cutting a four-sided object, cutting a square. Okay. And so that somehow came to English, and now we say square, right? So the root quad is also in our word square. And that's because geometrically, you might have heard, let's say, the phrase squaring the circle. Okay. So squaring the circle. So that's a phrase you might have heard. And this probably comes from the fact that, I guess, before algebra, if you wanted to find the area of a circle, you'd want to construct a square that has the same area, right? So you want to essentially create a square of the same area as the circle. And using compass and ruler, for example, this construction is impossible, as you probably know. Okay, so squaring, right, has to do with area. Okay. And so this is a good segue into what we really want to study here. We want to know what is calculus. Okay. And so I kind of decided to do maybe a more historical kind of approach here. So I'm going to look at a problem from, I guess, before our current era. So this is a problem that was solved by Archimedes. So, you know, about 250 before current era. Okay. And Archimedes wanted to compute, given a parabola. Archimedes wanted to compute the area of a section of this parabola that's cut off by just a segment cutting the parabola like that. So Archimedes thought about filling up this parabolic section, if you will, with triangles, because we know things about triangles. They're simple enough objects, and people who did geometry instead of algebra would be comfortable with triangles. So I'm not going to say how, but they would pick a point and they would draw a triangle. And that triangle has an area which would be easily computable. So far we see that the area of that parabolic sector is A, and then plus. And then we continue the process by building smaller triangles off the two sides of the original. So we have these triangles, and so this is the original. Let's say that's yellow. And then we have two new triangles in green. And it turns out that each of these new triangles can be proven is 1/8 the previous triangle. So we would have two triangles, two green triangles, each of which is 1/8 the triangle that we built off of. Okay. So that would say is green. And then we can continue the process. It's hard to see, but we can then, I shouldn't use A, I guess. But off the green triangles, we can construct new blue, let's say the blue triangles, right? And so how many of those will we have? We would have 4 of those. Okay, so we would just get double the, so 4 times. Okay, we have 4 blue triangles, and each of those would be 1/8 of the green triangle. So, and the green triangle has area which is so it's 1/8 the green triangle. The green triangle had an area of 1/8 the original triangle, and so on, right? And so you see that we can conceptualize that we can keep filling this parabolic sector with more and more smaller and smaller triangles. And this is a process that would continue forever, conceptually. Then so we would create new triangles. There are 8 of them, but that's going to be 1/8 the previous one. So the previous triangle had this area. So okay, and this continues forever, and what we can see is a pattern. I'm just simplifying here. Right, and we can continue this forever. So dot, dot, dot. We can take out the A. And then we're left with this sum, which, goes on forever, but Archimedes had ways of geometrically interpreting this, and Archimedes knew that this sum turns out to be 1 over 1 minus 1/4. Okay, you don't have to know this. Okay, so it turns out that the area of the parabolic sector is 4/3 the area of the biggest inscribed triangle, the yellow triangle. 256. Oh yeah. So these are powers of 4, and I just doubled. Thank you. Thank you, Elliot. Okay. Okay. All right. So, I mean, I guess 2 points here. There's this ad infinitum kind of process where we hope that conceptually, as we kind of pretend we're going, we execute this process forever. We fill the whole parabolic sector, and we get our area. Another point would be that this is way before Newton, right? Gosh. So the ideas, you know, calculus was built up from ideas that were already present, I guess, in antiquity. Okay, so, right. So here we used simple objects, like a triangle, and a, let's say, call it limiting process, to be able to say something about a more general or complicated, you know, curvy object. Okay. Oh, so how did I get this? Well, so you would have to know something, and you'll learn this about this if you haven't already in Calculus 2. So 2414 or 2419. So this is a geometric, the result of a convergent geometric series. So if you're interested in that, do a Google thing, right? It's a great topic which you will learn in Calculus 2, if you haven't. It should be, it's a 1 minus 1/4. So just to maybe see what I'm referring to, if you have 1 plus, let's say, I'll just call it r, right? Plus r squared, plus r cubed, and so on, and this goes on forever. Okay. This sum, that's called geometric sum, is equal to 1 divided by 1 minus the common ratio r. So in our problem, we had 1 plus 1/4 plus 1/16. So that's 1/4 squared, 1/64, so that's 1/4 cubed, and so on. 256 is 4 to the power 4. So you see that the r in our problem is just 1/4, but the minus is part of the formula. How do you choose the point that makes the initial triangle of area A? What is this topic called, if I want to? How do you choose the point that makes the... Oh, that is an excellent question. I believe Archimedes chose a point on the parabola such that if you draw a tangent, and now this could be beyond, you know, the scope of today, but you, well, not really, but you draw a tangent line that's parallel to this segment. So these two guys are parallel. So you choose that point of tangency. There's other more modern constructions as well. So this might be a construction you're more familiar with, but it's the same idea. You want to find the area of this kind of region, which is not a regular polygon, so it's more complicated. So can we use some sort of limiting process? Right? So, well, sure, let's just choose some points here. It's halfway, halfway, halfway. Okay. And maybe we can approximate the area with kind of regular polygons. So let's say, right, we can kind of try to fill in. Now, what kind of shapes are these, by the way? Does anybody know the name? Trapezoids, right. And so you have like trapezoid 1, trapezoid 2, trapezoid 3, trapezoid 4. And that, trapezoid is regular enough where you can, the, if you like, so here's the trapezoid. It has a height, if you will, and two bases, which are parallel to one another, right? And the area of that trapezoid is 1/2 b1 plus b2. So the average of the two base lengths times the height. Okay. But it's a well-known formula for trapezoid. So the area here of this curvy region is approximately the sum of the trapezoids, the areas of the trapezoids, right? But of course, we can make, and so this could be so the sum of these areas of the trapezoids is an approximation to the area we want, but there's probably some error. Like we see that trapezoid 1 underestimates the area, and maybe trapezoid 4, for example, overestimates the area because there's this extra bit here. I still don't know how to use Riemann sums in game development. Well, you just turn it into a puzzle for an RPG or something. I don't know. The shape of brute force. Okay. Right, but of course we could make this a better approximation by just using more trapezoids. Right, so maybe we can double the number of trapezoids. So I pick more points. And you get the idea. You get finer trapezoids. And you can kind of visualize that you get less error now as you increase the number of trapezoids. All right. So you'd have trapezoid 1, 2, and so on, all the way through trapezoid, trapezoid 8. Let's just imagine I filled in the rest. So the area, better approximation here would be to use more trapezoids, and the area is just the sum of all the areas of the trapezoids. Okay. And we see that as the number, we can write as the number of trapezoids increases, you see that the sum of the areas of all the trapezoids, I don't know how many there would be, like say n, approaches, my bad, approaches the area of our irregular region, if you'd like. Okay, the area. Okay, so this is a limiting process. Okay. So these first two examples, the Archimedean, I guess squaring the parabolic sector, or finding the area of this region. That's one problem in calculus that you'll see, right? And again, so that's like the area problem. And again, we used simple objects to learn, and a limiting process to learn something about a more complicated object. I guess I should also mention that notice that these segments here, they're parts of lines, and they could be used to approximate the curve. Okay, and I meant that as a segue into the next big idea from calculus, the problem of finding tangents. So. Okay, So this is, let's say, the tangent problem, another big problem. So we had the area problem, now we have the tangent problem in calculus. All right. So before calculus and algebra, you know, geometers might have been interested in constructing a tangent line to, let's say, an ellipse. So this is a picture of an ellipse, by the way. Okay, so I should maybe explain myself. So an ellipse is defined by 2 points called foci. And what we want to do is pick a point and then let A be the distance between the point and the first focus, and B be the distance between the point and the second focus. And the ellipse geometrically is defined as all points such that this A plus B business is equal to some fixed number, some constant. Okay, and so geometers would have constructed this tangent line. A tangent line just meaning that it just touches the curve, right? Doesn't go through 2 points, if you will. They would have drawn extended segment A, and then they would have proved that these two, the tangent is just the angle bisector between, let me draw these segments in orange. So between this segment and this segment, right? These two angles have to be equal. So once you can bisect an angle, you can construct this tangent, right? But this is before algebra, before calculus. Okay. Well, so, but, you know, when physicists started, you know, looked at the sky and stuff, I guess why are ellipses important? Does anybody know if you think of physics? I guess looking at the sky physics. Orbitals, right. So the planets, yeah, go around the sun in a basically elliptic orbit. Okay. So Kepler, for example, would have been interested in this, and so they had a slightly different perspective. So again, this is kind of historical. This is like the point of view of Newton or Kepler or somebody, where they would have thought of a particle moving in space in time, right? So at different times, you're different positions on this ellipse. And they might have reasoned that, okay, I know that A plus B equals a constant. So if I increase segment A by some amount, let's call that H, by what amount would segment B have to change so that we still have that the sum of the two lengths is constant? It's a trajectory, that's right. Well, you would have to decrease segment B by amount H, right? Because we have H plus minus H is 0, and so we'd still get A plus B equals C. So somebody that's like, you know, celestial dynamics kind of minded would say, well, okay, so if I increase A by some amount, it would try to, if you just, A would want to like increase along A. So let's call that maybe H A. So it's like a vector. Now then you want to decrease B, and so B would decrease, so we would say that it's shortening, and so we would draw this vector. You make that better. Okay. Well, probably that's in the way. Okay, and you see that the length of this change going in that direction would have to be the same as the decrease in the length of segment B. will be equal to h. So if you draw a parallelogram, kind of those two combined tendencies, if you like, or velocities, whatever you want to think of it, you would use the parallelogram law for adding vectors, right? You can draw a parallelogram, and the diagonal is the velocity of the object, if you will. Okay. And so then the tangent would have to go through the point on the ellipse in the direction of that quote-unquote velocity vector. Okay. This is more like physics. Again, my perspective here is in the introduction is just a little bit historical. Okay. Now, so for the next example, before we move on to the, talking about actual limits and finding limits. So this is the graph of some function of x. So again, from the perspective of somebody like Newton, you would have an object that's changing position with time. And so you would have, let's say, a change in the x direction and a change in the y direction. And because you know y is a function of x, maybe you can somehow relate those two changes, right, in the x direction and in the perpendicular y direction. Okay, and so then if you add those up using the parallelogram law for adding vectors, your tangent would, of course, pass through the point of tangency in the direction of that vector. So this would be a tangent. Okay, but the question is then, how would we want to relate the kind of change in, you go some amount in the x direction, by what amount would you go in the y direction, given that y is a function of x? Okay, so maybe here would be I'll present a more modern conceptualization of this. So we have some x value a, okay, and we want to kind of draw a tangent to the graph at when x equals a. So we would instead use a linear approximation, if you will, by picking a point nearby where, let's say, x equals b, and drawing a line through those 2 points. And we know that, 2 distinct points in the plane define a line, so this is not a problem. Okay, and this kind of line is called a secant line. Okay. So what would the calculus bit be here? Well, imagine that we let b get closer and closer to a. Okay, so for each such value of b that's getting closer and closer to a, we can always draw a secant line because we always have 2 distinct points. Okay. So where's the calculus piece? Well, we would hope, we would like, right, it would be a moral victory if the eventually as b gets arbitrarily close to a, the secant line at the end of this infinite process would become a tangent line. Okay. So we can say in words that as b approaches a, we see that the secant line approaches the tangent line. And the goal here was to not just use geometry, right, but rather knowing some equation that relates y and x, use that to algebraically, if you will, in a limiting process to get a tangent line. And again, finding tangent lines is important because we can approximate functions using lines near points. All right. Okay. So you have the area problems in calculus, if you will, and then we have the tangent line problems. So let's say, what can we say? The area problems broadly will be in calculus 2, right? So that's, I guess, 1326, 2414, 2419. Even though like 2419 will probably start on areas. And so this would be like the integral calculus. Okay. The tangent line problems is like Calc 1, right? So that's 1325, broadly speaking here, 2413, 2417. Yeah, so that would be, so this tangent line idea is related to derivatives, or it's called differential calculus, or just let's see, derivatives, or yeah, I'll just leave it at that, derivatives. So differential calculus. Okay. So by looking at some of these kind of problems in maybe from history, area problem, tangent line problem, maybe we can try to define what is calculus, right? So in all these cases we used, so this is a definition that I just kind of made up this morning, I guess. So we're going to use simple objects like lines, tangent lines, or polygons, triangles, trapezoids, to study, plus, I should say, the limiting process. So if something goes off to, we do something we do a infinite process, and hopefully at the end of it we come up with something finite. So limiting process to study more complicated objects. So I guess that would be something like curves, right? Like tangent line problem, and maybe more general regions. So that would involve areas, volumes, and so on. Okay. Okay. All right. So this is just I guess a joke or meme, right? Not just to make it simpler, because I don't want to draw too much. Let's draw a square where the length of the side of the square is 1. So what's the length of the diagonal? So the diagonal is square root of 2. Great. But what if we wanted, let's just pretend that we don't know that the diagonal is square root of 2, even do. And so how can we use the limiting process to approximate this length, right? What would be one attempt? Well, what we could do is create this kind of staircase pattern here. So if I take this yellow path, what's the length of that path? Well, the length of the path here, so the total distance as you travel along all the yellow segments. It's still 2, right? Because you're still You know, you have half, 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 and half. I took the midpoint, say, right? It didn't have to be, but so the so let's call that the length, yellow, right, is still 2. Okay, you might see where this is going, but then we can of course make the staircase pattern finer by taking midpoints and just making the steps smaller, right? Okay, so what's the length of the total length of the green segments? Yeah, it's still 2, right? You still have to go to the right the same amount, 1, and then you have to go up the same amount, 1. So you've traveled a total distance of 2. And you see where where this is going, right? Ah, crap. Right, there you go. You can again take midpoints and repeat the process. So now we can make an orange staircase that's even finer than the green one. And you see that the total length of the staircase, you can project the small line onto the main. Yeah. So if you take all the vertical, say, orange segments, my bad, you can project them onto the whole side here, right? So that, and likewise, all the horizontal orange segments of our staircase can be projected onto the bottom side. So that's still length 1. So the total length is 2. Now, if we do the kind of ad infinitum business, and we continue this, so continue the process infinitely many times, and what conclusion can we reach? Well, what we hope is that, you know, you expect this kind of staircase pattern to eventually get closer and closer to the diagonal, right? And at the limit, if you will, you would like that the staircase pattern converges to the diagonal, because they're getting arbitrarily close. But what's the problem here? What conclusion do we reach? Well, we know that the diagonal is square root of 2 from Pythagorean theorem. But we see that as, let's say, the staircase gets more stairs, if you'd like, gets finer, we might imagine that the staircase approaches the diagonal. And so you might conclude then that since the length of the staircase is always 2, and the staircase seems to be approaching the diagonal, yeah. So you get the conclusion that square root of 2 equals 2, which that's wrong, right? I mean, right? Square root of 2 doesn't equal 2? Right? If I square both sides, for example, I get 2 equals 4. So this is obviously wrong. It's a contradiction. Okay. So it's a joke. And the moral of this example would be that when you're doing a limiting process like this, you have to be careful. There are dangers. Things that seem kind of like they might work don't always work, right? So you just have to be careful. There's some details that you'd have to be aware of. Okay. All right. So what time is it? Great. Okay. Does anybody have questions so far? This was just an introduction. An overview of calculus, I guess, in a very broad sense. Okay. No, so this was just an overview of what calculus actually does, right? Simple objects plus a limiting process. Yeah, limits and derivatives. So the limiting process limits. And we use, and so we can talk about more complicated objects like curvy lines and so on. The tangent line problem is derivatives. Now, what did we do wrong in our staircase approximation? Yeah, I guess that would be a fractal, right? I don't know. It looks like it. I mean, that's a great question, right? Become a math major to see what went wrong. Okay. So, all right. All right, so now let's go ahead and look at things graphically. From this picture, this is just the graph of a simple parabola, y equals x squared. Okay. So with limits, what we're going to try to do is we're going to try to say what the behavior of a function is around a certain x value. So let's say x equals 2. Okay. So we're going to say, okay, so we'll suppose that, x is approaching the number 2. And by approaching, so this arrow, that reads approaches, right? So as x approaches 2, x squared approaches what number? Well, visually we see that x gets really close to 2. If you plug that x into your function, you get an f of x. And it looks like those f of x as x approaches 2 will approach the number 4. Okay. And it doesn't matter from which side, right? So x could approach 2 from the right-hand side. And you see that the value of the function x squared would approach 4. That's right. So we say that as x approaches 2, x squared will approach 4. All right. I think it's an intuitive idea, graphically. So the one thing we want to note here is that when we say that x approaches 2, it's important to to realize that x doesn't get to be 2. X is not 2. X doesn't actually get to 2. So x does not equal 2. So with this kind of analysis, this limiting analysis, we don't actually care what the function does at 2. So for example, here I used an open circle. So you probably all know that means that the function doesn't have a value there. F of 2 is not defined. But it doesn't matter with this kind of limiting process or analysis, because with limits, we only care about how the function behaves around a point, not what it does at the point. Right? It's a big distinction. Okay. Now, the way we're going to write this, I mean, this is a pretty good notation, right? It's pretty clear. As x approaches 2, x squared will approach the value of 4. But the way we write it conventionally is we say, okay, we're going to take the limit as x approaches 2 of our function, x squared. And the limit, the thing that x squared approaches, is equal to 4. Okay. So you use this kind of notation. So these are equivalent statements. This is what you'll be using. Okay. All right. So maybe we can, I'll draw a hole here to indicate that we really don't, with the limits, we don't actually care what the function does at a. It could be undefined. It could be defined somewhere, right? Like this, so this could be f of a. Okay. And we're going to use the notation that as x approaches a from either side, the function approaches some number. We call it L, so let's say that's limit. Okay. So we're going to write the limit as my x's are approaching a of the function. is equal to the limit. So this is what x is approaching. This is what f of x is approaching. All right. See if I, yeah, okay. So let's take another quick example. So graphically, what is the limit as x approaches 2 of our function? Okay, anybody? Yeah. So again, you know, if x is 2, f at 2 is equal to 3, right? This f, let me write that clearly. So the function at 3, at 2 is defined, looks like from the graph, it looks like it's defined to be 3, okay? But the limit is not 3, because again, with limits, we only care how the function behaves around a point. And it looks like as x approaches 2 from either side, f of x approaches the value of 1, so we say the limit is 1. Very good. I'm glad everybody got that. So I think we can skip the other points here. Okay. Now, if anybody has some experience with differential or limits, you might see that I'm kind of ignoring an issue here. So here, it seemed like that regardless of which side you approach a number from, right? So from the left or the right of that number, it looks like the function would approach the same limit. Okay. But it doesn't have to be the case. We have functions, for example, like, say this is the graph of y equals absolute value of x over x. Right. So first of all, the domain is all real numbers except 0, right? X cannot be 0 because you can't divide by 0. And we see that if, for example, we choose to see what the graph would look like, why the graph looks like it does. So if x were 1, for example, so x is positive in this case, we can say that the absolute value of x, let me just, I guess, do it with 1. So just 1 over 1 or 1, right? Because x is positive, we're taking an x that's like on the right-hand side. The absolute value of x is just equal to x because x is positive. So you see that y would have to be 1. So you get a constant function. And that's right, the limit actually wouldn't exist at 0. And likewise, if we take an x value, let's say -1 as an example, so x is negative, y would be, so x divided by, absolute value of x divided by x, this would be 1 divided by -1, so -1. And it turns out to be the case here for all x's that are negative, right? Since x is negative, we can rewrite the absolute value of x as the negative of that negative x to get a positive value. And so you get -1. Okay. But you see the problem here, that the function around 0, around the origin, the function doesn't behave the same way on either side of 0. Okay. So this says that we need to think about not limits. We have to think about the limiting behavior of a function as we approach a value from the left and the right. Okay. So for example, we can say, well, let's talk about the limit as x approaches, and I should probably use words here as well. So the limit as x approaches 0. Okay. Let me write that out first. So suppose, so as x approaches 0, from the left of the number line, or from the negative side of the number line, you see that absolute value of x over x, our function, is approaching what value? -1, right? Because as x approaches 0 from the left, the function is constantly -1, so that's the limiting behavior. Okay. Well, how would we, and then we can, from the right as well. So let x approach 0 from the right. So as x approaches 0 from the right of the number line, we see that the absolute value of x over x, well, the function always evaluates to +1 for positive x's, so this would be 1, right? Approach 1. Okay. Now, so these are called one-sided limits, right? Because we're approaching a value of x, and we're specifying whether we're approaching that value of x from the left, right, or from the right. Oops, I don't need to do that. From the right. Okay, so the notation we would use is still the limit notation. Limit as x approaches 0. But to indicate that x is approaching 0 from the left, or the negative side of the number line, we'll put a little minus superscript there. So that minus means from the left. That's superscript. So x is slightly negative, right? It's approaching 0, but it's slightly to the left of 0. And then we'll say our function, the limit is -1. So likewise over here, we're going to say the limit as x approaches 0, but from the right. And to indicate that we're approaching 0 from the right, you can think of that as approaching 0 from the positive side of the number line. So we'll put a plus here. And then the thing we're finding the limit of is the function absolute value of x over x, and that would be +1. Okay. So we see that these two one-sided limits, these are one-sided limits where you specify whether you're approaching a value of x from the left or the right. These are one-sided limits. Okay. Okay. Right. So so let me just then do this in abstract. Suppose we have limit 1 and limit 2. So we compute the one-sided limits. And the notation is x is approaching a from the negative or the left-hand side. And this is the graph of some function. So the limit of our function is, in this picture, would be L1, right? X is approaching a from the left. The values of our function are approaching L1. All right. And likewise, we can look at the limit as x is approaching a from the right. So superscript plus. It looks like our function would be the values of our function would be approaching L2. Okay. So if, like in this picture, the two one-sided limits do not agree, they exist. Does it make sense to write the limit as x approaches a of our function is equal to some limit? Can we say this? Does that make sense? Well, no, because the function isn't approaching a single value, right? It's approaching one value from the left as x approaches a from the left, and another value as x approaches a from the right. So if the two one-sided limits don't exist, I guess, or they're not equal, then we can say that the limit in general doesn't exist. So does not exist. D. All right. So here in our example, it would make no sense, right? So when we say limit as x approaches 0 without a superscript of our function, since the two one-sided limits are -1 and 1, those are two different limits, we can say that the limit in general does not exist. Okay. All right. So when we wrote the limit as x approach, so this is from before, we saw that as x approaches 2, our function approaches the value of 1. And we didn't have to indicate, there's no superscript. Right? If you're not indicating whether you're approaching 2 from the left or the right, what you're saying is that it shouldn't matter. As x approaches 2 from the left or the right, if we should be approaching the same number, the same limit. So the only time you would write, I apologize, this a very sensitive tablet, I guess. Right, so here the limit as x approaches 2 from the left of our function is 1, and also the limit as we approach 2 from the right of our function is 1. Therefore, only then can we say that the limit in general, regardless of which side you're approaching, exists, right? And it's equal to that common limit. Okay. So the limit in general, without specifying what side we're approaching to from, exists only if the two one-sided limits exist and they agree they're equal. All right. So we talked about the one-sided limits and what it means for the two-sided limit to exist. What time is it? 2:05. I guess it was suggested that we take a break, or like a 5-minute break or something. But what we're going to do in the next example, and I'll go ahead and give a 5-minute break, but if you want to keep kind of thinking, this is the graph of 1 over x, y equals 1 over x, and this is the graph of y equals 1 over x squared. Okay. And we're going to talk about the behavior of the function of our behavior of our functions as x approaches 0 from either the left or right. Let's think about that. And we'll be back at 2:11, if that's okay. All right, so we'll keep moving forward. Hopefully I won't lose my connection. It seems pretty bad right now, but it's okay. So far, so good. Okay, so now what we're going to talk about are essentially infinite limits. Which is kind of, yeah. 1 over x squared goes to 0. So here, for example, let's talk about what happens sort of as x approaches 0. On the left, what happens to our function? Our function is 1 over x. So I know that Elliot already did kind of primer on this, so I don't want to belabor the point, but we know that if you try to plug in x directly, you get 1 over 0, which is undefined. But if you take a non-zero number and divide by that 0 really indicates that the numerator is getting arbitrarily close to 0. So if you take 1 and you divide by a really small number, you're going to get a large number. So this is so we can say that if you get something like a non-zero number like 1 over 0, you're going to get either something that grows without bound, plus infinity, or minus infinity if it decreases without bound. Okay, good. All right, so maybe it's not a mind necessarily. Okay, so if we get a non-zero number divided by a denominator that's getting arbitrarily close to 0, so I'm putting this in quotes, of course, then we get either plus or minus infinity. And we should be able, we were expected to know whether it's plus infinity, so the function will grow upwards without bound, or minus infinity, so the function will decrease without bound. Okay. So we know they're going to get plus or minus infinity, and graphically we see it's negative infinity. But you can think of it as 1 divided by an x that's approaching 0 from the left, right? So since x is approaching 0 from the left, x is going to be close to 0, but slightly smaller than 0. X is negative. So we can think of this as a slightly negative x, yeah? Or no, it's a negative x, but it's close to 0. So positive number divided by a negative number gives you a negative number, so it must be negative infinity, as you can see from the graph. But decreases without bound. Okay. So then we say, infinite limits. We're saying that the limiting behavior of the function that it here it decreases without bound. So likewise, we can take a limit as x approaches 0, but from the right. So limit as x approaches 0, but from the positive side of the number line. Right. This would be like, in quotes, 1 over 0 that's slightly positive. And we know that positive over positive is positive. So this must be positive infinity. Yeah. As we can see from the graph, as x goes to 0, f of x increases without bound. So that's what we mean by infinite limit. And we see that this is going to be, you can probably anticipate that this is going to be related to vertical asymptotes. So as long as one of the one-sided limits is going to be an infinity, plus or minus infinity, then we're going to say that we have a vertical asymptote. And this is going to be the calculus definition of a vertical asymptote. And we'll see why we need this calculus limit definition of a vertical asymptote and not the pre-calculus one. Okay, in some examples. So, okay, so the limit from the left is negative infinity. And from the right, we go off to positive infinity. So what can we say from these two statements? Oops. From these two statements, what would we say about the limit as x approaches 0? 1 over x. Well, besides the two one-sided limits not existing, in the sense that our function doesn't approach some fixed finite value, but goes off to plus or minus infinity. Since these two infinite limits are different, so one is positive, one is negative infinity, we can say that this limit does not exist. Very good. Okay. Let me make a copy of this real quick. All right. So then I guess I'll try to move on to the next example. All right. So this is the graph of over x squared. And so we can find the limit as x approaches 0 from the left of 1 over x squared. So this is still going to go to 1 over 0, if you will, in quotes. So we know that we get non-zero over something that goes to 0 is going to be an infinity of some sort. But is the x squared going to is x squared approaching a positive 0? A positive 0? That's bad. Is it approaching 0, but is it slightly positive or slightly negative? Well, it's kind of like an x value that's slightly negative approaching 0, but you're squaring it, so any number squared is going to be positive. So that's going to be approaching 0 that's slightly positive. So we get 1 over 0, that's something that approaches 0 from the positive side. So this is going to be positive over positive. That's going to be a positive infinity. Okay. Similarly, the limit as x approaches 0 from the right-hand side or the positive side of the number line of 1 over x squared is still going to be 1 over a slightly positive 0 because anyway, x is positive and we're squaring anyway, so it's positive infinity. And so we could write then, because even though the limits, one-sided limits are infinite, so technically the limit doesn't exist in the sense that it doesn't, it's not a finite value, but because the limits agree from either side, we can say the limit as x approaches 0, regardless from which side, so you don't use the superscript, is positive infinity, right? So the function grows without bound on either side of 0. And we're not, I guess the way I think of it is we're not saying the limit exists, we're just kind of more clearly saying how it doesn't exist, right? Okay. So those are types of limits at infinite limits, right, where the function either blows up or blows down, so to speak. Okay. So next, I wanted to look at this function. This is the graph of natural log of x. And from the graph of this log function, what can we say? First of all, we want to kind of see what the log function does around 0 when x is close to 0. So first of all, is this statement, what I have written so far, you think correct, or is something wrong with that statement? So limit as x approaches 0 of log of x. Is there something wrong with that statement? Yeah, the domain of natural log is all x's which are strictly positive, right? You can only take logs, yeah, you can only take logs of numbers which are positive, strictly greater than 0. Okay. So that doesn't make sense because when you don't use the superscript to indicate which side you're approaching 0 from, you're implying that the behavior of the function, the function exists on either side of 0. So that's not correct. The best thing we could do is just compute a one-sided limit, and that would be a limit from the right, because log is only defined for x's which are greater than 0. Oops. It's weird. Okay. But from the graph, without knowing much about log, as x approaches 0 from the right, what does log do? What's its behavior? Well, it seems to be decreasing without bounds, so we'd say that it goes off to negative infinity. So you can say that because we're going to relate this to vertical asymptotes, that log has a vertical asymptote, meaning x equals 0, even if it's just from one side. All right. All right, so next what we can do is talk about the third type of, I guess, limit. So we talked about just regular limits as x approaches a number. And then we talked about infinite limits. So as x approaches a number, our function goes to plus or minus infinity. And now we want to talk about limits at infinity. So let's use log and exponential as a starting point. All right. So these are limits at infinity. So I guess more maybe precisely, these are limits of a function as x either goes to infinity or x goes off to negative infinity. So either x gets arbitrarily large, right? Because x is going off towards infinity, positive infinity. Oops. Then what we're saying is that x is just becoming larger and larger, and we just have to imagine what happens as x continues to grow. Okay. Maybe it's not that obvious from the graph of log of x, but we need to know familiar with these limits for all the calculus courses. So regardless of sequence. So the limit as x goes to positive infinity of the log function, it's not clear, but log does keep growing forever, even though it's very slow growth. Log still grows without bound as x becomes large. So we say that that's positive infinity. So we want to be familiar with that limit, because log is such an important function. Okay, so now what about the other graph, which is the graph of an exponential, basic exponential function, e to the x, y equals e to the x. Okay. So we about the behavior of the exponential function as x now goes off to negative infinity. So x is decreasing without bound. What can we say about e to the x? Graphically, as x goes to negative infinity to the left, what value is e to the x approaching? 0. Thank you. So I guess in quotes, if you'd like, you can think of e to the negative infinity as something that goes to 0, and it's in quotes because this is really a limiting process without me just writing the limit statement. But don't ever let the grader see that, right? Okay. And so likewise with the graph of our exponential function, what's the behavior of our exponential function as x goes off to positive infinity? Well, it looks like as x becomes very large, the exponential function, famously has exponential growth there, right? So it goes off to infinity, and it looks like it's positive infinity. So again, exponential function very important. So you want to know that as the argument of the exponential function goes to positive infinity, the exponential function itself goes to infinity. In quotes, e to the infinity equals infinity. Okay. Now these limits at infinity, so yeah, as x goes to plus or minus infinity, this has something to do with horizontal asymptotes. Right? Horizontal asymptotes are the asymptotic long-term behavior of a function as the argument of your function becomes very large or very negative. Oops, so limits at infinity have to do with horizontal asymptotes, as we'll define soon enough. Okay, so if the limit at infinity plus or minus infinity is some finite number, so for example, this is a finite number, it's 0, but infinity is not. If this is a finite number, this is just anticipating the definition of horizontal asymptote. If the limit is finite, then we can say that the function has a horizontal asymptote. It approaches some horizontal line in the long run. Okay. Okay. So graphically, what we've talked about are just limits as x one-sided limits. So x approaching a from the left or the right. And now if these two limits, let's say L1 and L2. So, and we said that if these two one-sided limits agree, then in general we don't have to indicate whether we're approaching a from the left or the right. And that would be the common limit, I guess, to say L. Okay. On the other hand, if the two one-sided limits do not equal, then we just say that the limit doesn't exist. Right? Because it doesn't make sense to talk about when you just write a without the superscript, you're communicating the idea that it doesn't matter which side you're approaching a from. So the two one-sided limits not agreeing means the limit in general doesn't exist. Okay. All right. Oh yeah. So this and then we talked about infinite limits, and that had to do with vertical asymptotes. And then we talked about limits at infinity, so as x goes to plus or minus infinity. And that's going to be related to horizontal asymptotes in calculus. All right. So let's look at this stitched together, if you can call it stitched together, thrown together graph of some function. And I guess we can use open circles. Oops. All right. So let's talk about the limit of this function, whatever it is. We see its graph as x approaches -1 from the left. So one-sided limit. So according to the graph, piecewise, what's OA? Can somebody tell me what OA, the acronym is? Oh, yeah, you can talk about non-horizontal asymptotes. So you can in general talk about the asymptotic behavior of a function. So just to quickly answer that question, if I may. So for example, if your function is, something very simple, then obviously as x goes off to infinity, say, and limit at infinity, the second term will go to 0, right? Because you get 1 over something that gets arbitrarily large is something that gets arbitrarily close to 0, but x will go to infinity. Okay. But the idea is that, well, this is infinity, so that's kind of strange. But what I'm trying to say is that for large x's, and x is going to get large, the 1 over x is something close to 0, so it's negligible compared to the x. So x plus 1 over x is just approximately x if x is large, whatever that might mean. Right. So we can we can graph the line y equals x, and the idea is that as x goes off to infinity, the values of our function are approaching this diagonal line y equals x. So we can say that that line is like the asymptotic long-term behavior of this function. Okay. And there's nothing stopping us from, instead of saying that our function gets close to some line, we could maybe look at the function x squared plus 1 over x, right? The limit is infinity, but you can say that for large x's, the x squared term is going to dominate, if you will, if you don't mind that kind of talk. This will be close to just the x squared, right? Because 1 over x, as x gets large, is something that's negligible. It's close to 0. So then we can say that the asymptotic behavior of this function is something that approaches, so here's the parabola y equals x squared. So yeah, as x goes off to infinity, we can say that our function approaches this parabola, right? So that's it's asymptotic behavior. Yeah. Okay. All right. So back to the kind of quiz, so to speak. All right. Yeah, this is a graph of some contrived piecewise function. Okay. I'm hearing myself for some reason. All right. So as x approaches -1 from the left, what value does our function approach? Looks like it's 3. Very good. So then the other one-sided limit, as we approach -1 from the right, so plus, we see that the function approaches the value of 4. Okay, and because we're talking about limits, we're only looking at how the function behaves around x equals -1, not what the function actually does at -1. Okay, so we don't care that the function at -1 is defined to be, it looks like it's approximately 3.5, let's say. That's irrelevant. Okay, so then we say that the limit in general, as x approaches -1, without indicating from which direction, does not exist because the two one-sided limits don't agree. Okay. So what about the limit as x approaches 2? Does that limit exist? So here's x equals 2. Yeah. Right. It exists and it's equal to 1 because the two one-sided limits exist, and they're both they agree. Yeah, they're both 1. All right. So great. And it doesn't matter that the graph is not smooth there. You have this sharp turn, this cusp, if you will. Okay. Great. So what about the limit as x approaches? What can we say about the behavior of the function at x equals 5? Or around x equals 5, sorry. Okay. So the limit as x approaches 5 from the left, if we can still read this graph. is going to be 4. Yeah, x is getting close to 4. I mean, it's 5, sorry. F of x looks like it's getting close to 4. All right. And what about the limit as x approaches 5, but from the other side, the right-hand side? Graphically, we see that the function grows without bound as x approaches 5 from the right. So it goes up. Yeah, the graph goes up. So this limit looks like it's positive infinity, so to speak. I guess the limit doesn't really exist. So the limit in general won't exist, right? What would be the equation? Because one of the one-sided limits is infinity, we're going to define that to be the condition in calculus that gives you a vertical asymptote. And so what's the equation of that vertical asymptote? A vertical asymptote is a vertical line, so it has an equation. So y equals 5, sorry, x equals 5, oh my lord. Okay, x equals 5 is a vertical asymptote because one of the one-sided limits is plus or minus infinity. All right, and I think we don't have to do the last two. I think they're pretty clear, but I'll write it out anyway. The limit as x approaches 9 from the left is positive infinity. The limit as x approaches 9 from the right, plus superscript, is negative infinity. Okay, the limit doesn't exist. Okay. And we see that the limit as x approaches 13 from either side is plus infinity. Yeah, the function blows up on either side of 13. So we can see that we can write that the limit as x approaches, the function goes off to infinity as x approaches 13 from either side. Okay. So do the one-sided limits always exist? No. So yeah, the problem is when the limit is plus or minus infinity, right? When the function blows up or blows down, the limit technically doesn't exist. So for the one-sided limits to exist, you have to have that the one-sided limits are a finite number, not infinity of some sort. So no, the one-sided limits don't have to exist in the sense that they can go off to plus or minus infinity. And that's actually a good question. It might not exist for other reasons. So for example, if you have a function that keeps oscillating, let's say we draw a sine function, right? Whatever. Okay. So let's say that this is the graph of y equals sine of x. So as x goes to infinity, what can you say about sine of x? Well, not very much, except that it keeps oscillating, right? Sine of x will always oscillate between plus and minus 1. So it never settles down, right? It doesn't converge to doesn't approach a single number, a y value, if you will. So this limit doesn't exist because the function keeps oscillating. So the limit might not exist if the function just never settles down to any one specific number. It just keeps oscillating, for example. All right. Great. Whew. All right, so then maybe we can start using undefined at vertical asymptote. Yeah, when you have a vertical asymptote, at least one of the one-sided limits doesn't exist in the sense that it goes to plus or minus infinity. All right, let's see. So now we kind of want to leave the graphical part, right? And then learn how to actually compute limits when we have the function presented to us algebraically. So for example, so we have some function. I think this was, yeah, okay. And suppose I'm interested in the limit of our function. Oops, sorry. As x goes to 1. Now, graphically, we see that if, so this is the graph of our function, by the way. So if when x equals 1, the function is equal to 3, and it looks like it's a nice and connected graph, so we expect the limit to be 3, right? As x approaches 1, it looks like the values of f of x approach the number 3. Okay, so what you always want to try first is try to evaluate directly. That's the kind of first thing. By plugging in the value into x that x is actually approaching. So you can always just try that. And so if x goes to 1, let's say x gets really close to 1, so it's like practically 1. So we're just plugging in for x the value that x is actually approaching. Okay. And in the numerator, we get e to the 0, which is 1, plus 5 times 1 divided by 2. So the limit is indeed 3. And this is great, right? If you get, if you're not dividing by 0 and you get some finite number by evaluating directly, you found the limit. And this has something to do with what we call continuity, which we'll discuss next one. But you can always try to evaluate directly. If you get a number that's finite, that's the limit. Okay. So notice we weren't doing something like dividing by 0. Okay. And you're probably in class also be maybe at the very beginning expected to actually maybe use some kind of algebra package or something, and actually plug in values of x, right? So as x goes to 1, x is really close to 1, so we can choose values of x which are closer and closer to our target. So we can approach 1 from, well, if I say below, that's going to be weird. From the left-hand side, and then we can approach 1, x can approach 1 from the right-hand side. And if you, then I plugged in x into our function, and we see that we get values of f of x that converge, that approach the number 3. So numerically, if we use a calculator, we can see this limit is indeed 3. Yeah. Sine of 1 over x is probably the best example. I just didn't want to, for the one-sided limit, yeah. Okay. So Elliot pointed out that, well, let's just continue. Okay. So we can try to evaluate directly. We get a finite number, we're done. Okay. 1 second, let me scroll down my outline. Okay. So what happens if we try to evaluate a function directly and we don't get a finite fixed number? So for example, this is as simple as it gets, I guess. So let's look at the function x squared plus x minus 6, all divided by x squared minus 4. Okay, and let's try to find the limit as x approaches. Okay, x approaches 4. Okay, so if you plug this in, sorry, x approaches 2, my bad. So if you try to evaluate this directly, you're going to get 2 squared plus 2 minus 6 divided by 2 squared minus 4. So you're going to get a 0 on top and bottom. Okay. And I think Elliot already mentioned that 0 over 0 is something that's nonsensical, and it's really not clear what the heck that means if the numerator and denominator are both going to 0, which is, is the top or the bottom going to 0 faster. So this doesn't tell us anything really. So we call this an indeterminate form. So indeterminate means the limit might not exist, or it might. And if it does, we don't know what it is. So this is an indeterminate form when you try to evaluate the limit directly. So what that tells you, this indeterminate form tells you, is that you're going to need to do some algebra before computing the limit. So the second kind of technique we can use is to just use algebra to factor, say, if possible. And this is, of course, something that you might want to think about if you have like a rational function, polynomial divided by polynomial. It's not the only time, but so we can factor. And yeah, I do plan to go over this theorem and sine x over x, but next time. Okay. So we can factor the numerator. And the denominator. Now the denominator is a difference of 2 squares, correct? So if you have a number squared minus another number squared, that's literally a difference of 2 numbers squared. So we all know from algebra, or we should know, that this is going to factor into a product of conjugates, right? So the conjugate for a plus b is a minus b, or conjugates of one another. And that's what the denominator was. X squared minus 4 is a difference of 2 squares. Just as a reminder. Okay. So once you factor, you can simplify, and you can say that, all right, these sort of cancel. Well, they cancel, right? Remember that x is not equal to 2, right? Is that clear? Right? Because x is approaching 2 with limits we don't actually let x become 2. So when x is not equal to 2, the original function is equivalent to the simplified function. The x minus 2 is canceled. And now we can try to reevaluate the limit directly by now letting x go to 2. So we get 2 plus 3 over 2 plus 2. So that's a finite number, 5 over 4, so that's the limit. So we had an indeterminate form, doesn't tell us whether the limit exists or not. We factored, so some simple algebra, simplified, and then we evaluate the limit, and we see that we do get a finite number, so the limit is that finite number. Okay, so you can factor. All right. So let's maybe look at another algebraic technique that will help us to resolve these undeterminate limits, or a determinant form. So maybe we can multiply by conjugates. Okay. Let me write the example first, or rather motivate it, I guess. So the limit as x approaches 4, square root of x minus 2 divided by x minus 4. So this is still an algebraic function. If we try to evaluate directly, of course, we're going to get 0 over 0. Right, so we get 0 over 0. So that's indeterminate. The limit might exist, it might not. So we want to use algebra here to rewrite, kind of re-express our function, so we don't get an indeterminate form. All right, later. Okay, so what can we do here? Well, we did mention difference of 2 squares, so yeah. Okay, so we mentioned this difference of squares factoring. And so conveniently, if So I guess if you have multiply two conjugates together, right, you end up with a difference of two squares. So if you have a square root, this is very convenient. So if you have square root of x minus 2, and you multiply by the conjugate, we know that if you FOIL this out, or by the formula above, we get the first term squared minus the second term squared. So by multiplying something that has a square root by the conjugate, you might be able to get rid of the square root. Okay? So multiplying by conjugates can get rid of square roots, so that's something you want to keep in mind. Okay? So here we're going to multiply by a conjugate. And again, if you have square root, you might want to consider that possibility. You want to multiply by the conjugate on top and bottom of the thing that has a square root, so the square root of x minus 2. So we're going to multiply the top by the conjugate, square root of x plus 2. And of course, we have to multiply the denominator as well by the same factor. Okay. And so in the numerator, because we're multiplying conjugates, we get square root of x squared, so that's just x, minus 2 squared. And in the denominator, we already have the factor x minus 4, and now we have this additional factor, square root of x plus 2. But you see, because x does not equal 4, x is only approaching 4, this does indeed, this expression is equivalent to what you get after you cancel. But now we can just evaluate the limit directly, and we do it here. So x goes to 4. So suppose x is 4, let's say. So this gives you 1 over 4. So that's a finite number. So we started with an indeterminate form. We saw a square root, so we tried multiplying by the conjugate, and it happened to work out. The pesky factor they gave us is 0, and the denominator especially just canceled something in the numerator, and we were able to reevaluate the limit. We get 1/4. All right. I guess one more thing about conjugates. This is for the people who are not going to take 1325. So if you're taking 2413 or 2417, there's another, let's say, call this 3.5, yeah? Or 2.5. Okay. How did I go? Oh, 1. Oh, yeah, 1, 2, so 3.5. So you can, again, multiply by conjugate, but in a different situation. Okay. So here, we're going to take a limit as, we're going to take the limit of cosine squared, so trig functions, divided by 1 minus sine of x, as x goes to pi. Oh no, pi over 2, sorry. Okay, so we try to evaluate the limit directly, and we get cosine of pi over 2 squared, divided by 1 minus sine of pi over 2. And so, unsurprisingly, the cosine of pi over 2 is 0. 0 squared is 0. And sine of pi over 2 is 1. So we indeed get 0 divided by 0. Indeterminate form. So why would I want to multiply by the conjugate here? And the conjugate of what? Well, if we have 1 minus sine squared, there's a Pythagorean trig identity, right, that tells us that this is equivalent to cosine squared. So it's a trig identity. But notice that we can think of the left-hand side as a difference of two squares. Oh, I got to go after this example. Right? So if you see a 1 minus sign or a 1 plus sign, you can always multiply by its conjugate, right? Of course, making sure everything's balanced in your algebra, because that will give you the Pythagorean trig identity. Okay, so let's try it. So if you have a like 1 minus sign, 1 plus cosine, let's try just multiplying the top and bottom by the conjugate of 1 minus sign, which is 1 plus sign. Multiply the top and bottom. Right. It's 3 o'clock, so thank you for attending, and tomorrow we'll talk about squeeze theorem. We'll go ahead, use some algebra for limits at infinity and infinite limits. Squeeze theorem, some special trig limits that are going to be useful. Okay, so here the denominator via our Pythagorean trig identity is going to become cosine squared. Oops. Okay, so of course cosine, well, x is not pi over 2, so cosine of x is not equal to, okay. Let's just say these cancel at the end of the day. And let's try to reevaluate the limit. And here it's obviously 2, because sine of pi over 2 is 1. So we evaluate this directly. All right, thanks for attending. We're not going to be discussing chain rule or any of the differentiation rules in this. Oh yeah, you could have, for sure, that's a good observation. So instead of multiplying by the conjugate so as to introduce the Pythagorean trig identity, we could have just said cosine squared is 1 minus sine squared. And then, because that's the difference of two squares, factor into conjugates, and you would have the same cancellation. So thank you for that. That is a good approach. Thanks. All right, and that's it. And I need to go to a meeting. Thank you so much.